All right. Sorry, getting my projector warmed up this morning. So this was posted as a link, but then I decided that, it seemed like a lot of y'all have been kind of into this MO theory. So I went ahead and printed it out. Oh, come back. There we go. No, come back. There we go. All right. So yeah, grab a copy of the paper. But now we're finally going to go through our sea of electrons. And so first let's kind of look at what your book presents it as, and then we'll look at why the paper, what is going on today? I don't know why the projector is finicky. Okay, but yeah, so we'll look at why the paper gives us just a little bit deeper understanding of exactly what we're talking about here. And so looking at this, okay, so now this is band theory. Again, this C, so we'll explain in just a second what it means. And so this band theory is trying to kind of put together, again, I'm going to summarize what this says, and then we'll look into more detail of the paper so we get a really good understanding. But basically now we're trying to model how we have the solid state structure and then obviously the properties that arise. And so when we look at the paper, this will kind of become a little bit more evident what we're talking about. And so, right, we want to be able to look at metallic solids. And so this could be, so your book, right, gives it as lithium metal or different metals. So why are metals conductive? And then we also want to be able to understand the properties of covalent compounds, which, like I said, the paper will tell us more. So looking at like graphite versus diamond, again, in terms of conductivity or not. All right. And so let's kind of read this. And like I said, we'll look at these pictures. And so this band theory takes our view. So we're starting with our atomic orbitals. But now our atomic orbitals are shared by our entire crystal structure. So there's the idea of the delocalization. And so, okay, just like before, atomic orbitals combine, right? We have a bonding and anti-bonding orbital. And so now just thinking about, now we have lots of n atoms, right? Like n number, sorry, that's not clear. So n number of atoms. And again, let's just kind of focus on lithium, or this, they have shown sodium, but one of our alkali metals. Okay, so our sodium, and it has this 3s1, right, valence configuration. And so, okay, we have n number of sodium atoms. And so now all these atomic orbitals combine. So we have n total atomic orbitals. And then that means, right, half of those, so this is just same thing from our atomic orbital principles, right? We start off with 2, we get a bonding, we get an anti-bonding. So same thing when they're delocalized. So half of them are going to be bonding orbitals. And then the other half, again, delocalized all across, are anti-bonding. And then the question is, right, again, how do the electrons fill up? And so looking at just our simplified model from sodium here. So now looking at our sodium, and we'll look at this in just a second. So our sodium in our, again, sodium metal crystal, so in our metallic state. So it's delocalized across our entire crystal lattice. And so then, and right, we have lithium here. And so I'm not sure your book explains this that clearly, which is why I like the paper. The paper breaks it down way better. But essentially what this is saying, okay, well, we have our sodium atom. It's half filled, right? Of course, we remember the S can hold 2. So it's half filled. And so that means that our sodium And I'm trying to draw this. So it's going to fill, right, its valence or bonding orbitals. And then the fact that half of them are occupied, right, because again, it's going to fill in with the lower electrons. We only had half of the total number in the S, so half are filled up. And so now that explains why sodium is conductive when we have this small band gap. And again, the paper kind of explains it a little bit better. And so looking at this, right, we have our occupied orbitals, so that's our valence band. And then whether something is conductive or not depends on that gap between it. So if it's a small or negligible gap, right, then you have a good conductor. And then obviously something large will be insulator. And so this is kind of the level we need to know for our class, essentially. So conductor, again, no energy gap. Semiconductor, small energy gap. And then insulator, large. But this really doesn't give us like a good picture of things, or isn't really a good explanation. Plus, there's some extra considerations that we need to take. So that's where we're going to switch to the paper now, because I think this does deserve good treatment of such. And so blah, blah, blah. So we start off with our alkali metals. And so it gives us, right, the presentation here. And so part of why you start to get things being conductive, so notice, right, so you have this initial band gap between your 1s and your 2s, but then things tend to be conductive potentially if there's overlap. So notice, right, in the 2s and the 2p, you have overlap. So now, right, that's going to make things conductive, at least, again, just with kind of this simplified atomic orbital approach. And so now let's look at this. And so I do recommend just kind of reading through the paper. And so let's look. So right, it's just showing us why this is so with our band gaps. But let's stick to, okay, so this is interesting here. And so it shows us some things. So helium, right, so compared to, so we'll look at hydrogen in a second, because hydrogen actually isn't that simple. But looking at helium, so helium, we remember, is 1s2. So right, this is our bonding, this is our anti-bonding. So this entire thing is filled, right? And then this is a large gap then between your valence electrons and then your lowest unoccupied. And so this correctly explains why helium is an insulator. Okay, that's fine. And then we had taken a look at our sodium before, so now let's just revisit that with lithium. So core, right, our 1s, but then our 2s, that's our valence for lithium. Again, think back to lithium. So 1s2, 2s1 for the electron configuration. So the s orbital half filled. So that means, right, we have a half filled band gap here. And that means, right, lithium is going to be conductive since it can easily go up to this anti-bonding orbital, right? So that is our conductive band gap. And so then moving to beryllium. And so beryllium could have given us some issues if not for this overlap. So now thinking about beryllium, so 1s2, 2s2 for the electron configuration. And so you notice, right, this is filled. And so you might think, wait, is beryllium an insulator? But no, right, we have this overlap here between the 2s and the 2p orbitals. And so that means that we have our conductive band gap there. So does that kind of make sense so far? Just kind of take it in for a second. So this hopefully makes sense. Again, you guys have been doing a pretty good job with MO theory. And so let's look at where things kind of break down. And so the paper kind of makes this point. So, okay, this has been great, right? These solids as atomic crystals. So this has served us well. Okay, now let's look at diamond. And so the problem with diamond, at least in this atomic orbital approach, is that it doesn't correctly show that it's an insulator. And so it tries it by two different methods here, just initially, right? So you can kind of see what they've sketched out in the paper. It's like, okay, let's just take it as an atomic orbital here on A. And so just thinking back, so we have 4 valence electrons for carbon. And then, right, we said there would be overlap. And so technically, with this diagram, this shows a conductive band. However, right, that does not match experimentally with what diamond is, right? So we know diamond is an insulator. So something is wrong here with our assumption of how we've drawn this. And so, right, that's the point that we're always emphasizing is like chemists kind of run with a theory, we run with a theory. Oh, now it breaks down, so now we have to figure out, right, where we have to make a little refinement of our theory. And then they tried a different approach. Okay, let's just simplify everything as our sp3 hybridized, right? We remember that happens. But you still have the same problem. So then you have these delocalized, right, sp3. So these are all the bonding. This is formerly anti-bonding. They're still half filled. And so you still have this issue where it's suggesting that diamond is conductive when it's not so. So, okay, now we're trying to figure out how we can approach this. And so then the switch is, okay, well, now let's consider whether we treat something as a molecular crystal or an atomic crystal. And so now we can go back to hydrogen and kind of our assumptions about hydrogen. And we may have different scenarios. And so shown here, right, is our molecular orbitals for hydrogen. And so we can show them, right, so they've made their bonding orbital. And so now this is showing that hydrogen as a molecular crystal is an insulator. But what about hydrogen as a metallic structure, right? So this is kind of showing us too what's the difference between, again, like fundamentally a molecular crystal and then our metallic. And so this is metallic hydrogen, if we were to treat it as such. And so that's what's shown here, right? So 1s1 for hydrogen. Now we have our 1s, so bonding, anti-bonding. So if we were to treat hydrogen as metallic, right, this would actually be conductive then. And so this paper was written in 1971. So at the time, they hadn't discovered metallic hydrogen. But somewhere in the paper, they surmise that this may be on like Jupiter or Saturn. And so later you can look it up and like, yes, there is evidence, right, of metallic hydrogen. So this sort of treatment is correct in thinking about it, right? So again, they're going to have different properties depending on the solid structure of hydrogen. Whether it's solid, again, as a molecular, right, diatomic H2, then it is an insulator. Or if it's under enough pressure, so again, in outer space is where we can find examples of that. But in extreme pressure conditions, then it actually does a metallic form. Okay, so that's interesting. But that still doesn't answer our diamond yet. And so now let's look at diamond. And so now what they've done is, so now we've taken kind of our sp3 hybridized orbitals, and then they add them right with our carbon here. So they kind of treat it separately. And this is like eventually what you do like in higher orders of chemistry. But essentially what they're showing is, right, they're showing how these, so right, of course diamond is tetrahedral, and those balls should all be carbon. But it's basically taking these 4 sp3 carbons and then combining them right with this carbon here to give us our new kind of molecular orbital treatment of that. And so this is what they get from this, right? So now we see that this sigma bonding sp3 band is filled, right? So that means that if you were to technically write this out, so that would be the bonding and then anti-bonding are both filled of the sp3. And then, right, you have more sp3 anti-bonding up here. But then this is what makes it an insulator now. And so now, right now we can see, okay, once we put together those 2 structures, so again, our carbon plus our 4 balls, right? So our 4 carbons, and kind of, again, the mathematical conclusion of that. And so now that shows us our band. So that's pretty interesting. And then what's kind of even more interesting is the treatment of graphite. And so let's find what's significant about graphite. I'm trying to find it in the text. So basically graphite is semiconductive. I'm trying to find the exact wording here. Here we go. I just missed that. So it says, okay, let's try this with graphite, right? Because again, we want to make sure that this molecular treatment is correct, right? So again, our kind of molecular solid versus, again, the atomic one. So seeing if this is correct, right, let's look at another property. So it mentions that the electrical conductivity of graphite crystal is anisotropic. So that means, right, it only goes through a certain plane. And so we can skip to kind of the good part over here. So then they've drawn it out. So again, our carbon center, and then we have our sp2 hybridized with our graphite, and then combining those. And so we see this small band, right? So most of them are insulated, but you can see this small unfilled 2p pi bond. So that is unfilled. And so it says that if the electric field is applied perpendicular to these planes, then the conductivity is observed. And so again, that's explaining why we do have small conductivity from that band gap there. So that's pretty interesting. And then that being said, you know, I'm pretty sure you can quantify this with the band gap and the different materials, and that would be, right, a whole area of research. And then, of course, that's where, like, the doping comes in. I think your textbook mentioned that. Oh, maybe not. I would have to look at your textbook. But essentially, there's something of doping where basically you take your regular substance and then you can swap out different materials. So like usually, like if you have some sort of silicon-based material, you can put like boron in it to make it electron deficient. or you could put like phosphorus typically, or maybe like arsenic, and then that gives it, right, more electrons. So extra. And so being able to tune that can also help, make different uh, like chips, change again the conductivity, right? If you're trying to dial in something. So basically that's how you change your band gap here as well by this doping method. And then so kind of finishing up this, so this just shows like different types of crystal arrangements. And so A just shows a nice ordered crystal, again like we kind of saw earlier, where it actually has a defined crystal structure, right? So going back to these, again, not inclusive, but our simple cubic, body-centered cubic, face-centered cubic, so anything with order. And then liquid, of course, is going to have more degrees of freedom, so that's just kind of showing how they're sliding past one another. Smectic means that they're arranged in more layers of our crystals, so then that kind of speaks to the 3D packing structure more and how it stacks. And then nematic means that they're aligned, but then they're not arranged correctly in layers. All right, let's look at other bits of the chapter. Actually, let's go back and do some math with this. So going back to this section here, so I just kind of teased what we're going to do, but let's look at a practice problem. So we have our example. And so your question is going to typically go like so. So you have your element. So in this case, we're looking at copper. And then I'll tell you how it crystallizes. So which crystallizes as a face-centered cubic lattice. So think about what that means, right, in terms of atoms and how the length, and then has a density of 8.96 grams per centimeter cubed at 20 degrees Celsius. So calculate the crystallographic radius of the copper. So how might you do that? Yeah, 20 degrees Celsius. Uh, well, you're trying to find the radius of the copper atom, right? But you're given the density. Sorry. Yeah. And then what other little part do we need? So density, so equals mass over volume. Yeah, so how many atoms? And then yeah, we'll have to put that over Avogadro's numbers. Now we're on the right track. So we can, probably the easiest way to handle this is we can take our molecular weight of copper, so 63.546 grams per mole. And then, okay, y'all had told me that there are 4 atoms, and then I'll multiply it by the mass. But then I'm going to get rid of moles, right? Because we're talking about individual atoms in our unit cell. So divided by Avogadro's number. And so now we can solve for volume, it looks like. So now plugging in, so 8.96 grams per centimeter cubed. Sorry, let me pull up my calculator. Oh, so then looks like answer in the chat is the final answer. So let me catch up. So plugging it in. Oops, sorry. All right, so then this should be our volume, correct, of our tiny cube. So then we have volume is 4.71 times 10 to the negative 23rd centimeters. And so then we could plug this into volume is length cubed, which then gets us into the radius. So I'd probably start by taking the third root of this. And so then this gives us our L, so 3.8, or 3.61 times 10, negative 8 centimeters. And then we said our length was equal to 2 times the square root of 2r. So just divide by this to solve for r. And make sure to put this in correctly with the parentheses and all that. And so I get what the chat got. And then do we get that in here? And we are in centimeters still, or at least I am. So about 1.28 times 10 to the negative 7, or negative 8, I don't know why I said the wrong number, centimeters. Do we all follow in class here? And yeah, so kind of Yeah, and it's always just in a square, right? And then, yeah, so we got our shape, and all that really told us was whether it's 1, 2, or 4 in there. And then for these problems, I'm always going to make it like a single atom, right? Like copper, polonium. We're not going to do sodium chloride, and then you're like, well, how many sodiums, how many chlorides, right? So we'll keep it simple in that sense. And then, yeah, you're given the density. So then you have to set up this density equals mass over volume, where again, you're calculating your volume of the unit cell. So that's where this came into play. Solve for volume, right? Mass divided by density. That's also what we were doing here. And then again, just getting the mass of the individual atom with this correction. And so yeah, the only variations you'll see of this problem are again, how many atoms, and then going back to the edge length. So whether the L, right? So this is going to be L then. So L could either be 2R for simple cubic, or L is 4R over the square root of 3, or this one. So that's the only subtle differences. So yeah, that's how we'll treat this kind of section. Let's see, how are we doing on time? So I think we just need to finish up a little bit about colloidal mixtures and any other kind of random loose ends. So colloidal mixtures just refer to when you have these particles are large enough to scatter light. And so usually they look like nice and shiny. And I'm trying to think, like some of you may have seen some nice crystals, like if you remember with the copper lab, especially when you started making like the copper oxide, like maybe some people, you can shine the light, right, and it's kind of like shiny. So that's kind of what this is going for. So if you were to dissolve like some sort of substance, so this was, right, like aqua regia or something of gold. But if you were to shine a light to it, right, it should be nice and glittery and shiny, and that is the Tyndale effect when it's scattering that light. And then this effect takes place in other mediums as well. So you guys have experienced this with like fog and mist, so that's why it's hard to tell like where the light is coming from, just from the scattering effect, again, of the Tyndale. So it just has to do with the particle size. So you can have the same effect with like a gas and a solid, like smoke or dust. And again, you probably have seen that. So I don't know if any of you smoke. So if you smoke, you've certainly seen the Tyndale effect. Or, you know, maybe you just start beating up your cushions and the sun is streaming in and all the dust flies up and it kind of scatters the light around. So that's the Tyndale effect. And then there are other just different mediums. So we have like a liquid gas systems, so foam, like shaving cream, liquid liquid, so obviously, right, these are all going to be paints, and or liquid solids, again, right, paints, and you could definitely be a paint chemist if you wanted, and literally watch paint dry as a job. And so, right, again, any pigment is a wonderful compound. And so you can, again, kind of see the particle effect when you've like mixed paints before. And then other mixtures, so we can have like a solid and a gas, like a pumice stone, right? Obviously leaves those holes. Solid liquid, like cheese or gelatin. And then solid solid, so just reminder that like gemstones are all because of like minor impurities that give you pretty colors. Yeah. I don't know why I thought of this for some reason. Of all the examples, so did you know that you can like be cremated and then turned into a diamond? Yeah, so some people know that. And then like I haven't seen this, but like I've heard people say though that like if you get a synthetic diamond that way, it might turn out a little bit of blue from like boron impurities. So yeah, just fun fact. things things to because we have boron in our bodies. So yeah, it's just like a significant impurity, and I guess like people's boron levels vary. So like they're different, and that's what I've heard that like these diamonds can vary in like how blue they are. I haven't tried it out. But well, that apparently that gives it like the impurity, because yeah, it's all about like what will give rise right to whatever impurity. So going back to however the electronics have to be, yeah. I don't know, but I mean, you can look it up. Like, you can do your pets too, like, technically. So, yeah. Anyways. Yeah, that's what I was saying. Like, fun fact of the day. There's always fun facts. So now let's look at soap and how soap is made. And so soap we'll probably talk about a little later. But soap involves a saponification reaction. Sorry. I forgot that if you just try to look up. And so let's kind of get an idea of what a saponification reaction is. And so essentially you have your fat, right? So some sort of fatty acid chain, and they generally look something like that. Right? Could have different bonds. So I was trying to pull up olive oil. So I don't know how much you guys know about soap making or not, but you can basically make soap with any sort of fats, right? So like way back in the day, actually what they used to do is like take, it's called soda ash, right? Like all the leftovers from your fireplace, and then you mix them with any sort of animal fats you had around, and there's your saponification reaction. Obviously, they weren't doing it very stoichiometrically back in the day, so this often produced pretty harsh soap. Um, but yeah, so the point being, again, we have this long fat chain, so that's going to be our non-polar group, right? And so this is what this is showing here, that we have our long hydrocarbon chain. And then once we do this saponification reaction, and sorry, let me just copy this picture over. And so our saponification reaction, we add a base, so typically sodium hydroxide or potassium hydroxide, again now to do it stoichiometrically. And so you can see that it deprotonates our acid here, and then it makes a salt. So there's our salt, right? So now this is our polar group. And so now this is showing how it's going to mix, and now how this works to actually solubilize and how soap works. And so it's called this little micelle that forms. And so you can see where the nonpolar hydrophobic ends are in the center, right? And they're going to be sopping up all that grease that's also hydrophobic. So hydrophobic. So right, this is not miscible with water essentially, but then it gets washed away since it forms this micelle, which literally like encapsulates our grease here, and then again our polar group on the outside, so that it solubilizes with water. Yay! And so that's soap there. Yeah, A lot of things like have that structure, right? Like that's how you kind of work in a cell and like get around things. Like how do you have a hydrophobic end and a hydrophilic end? And yeah, pretty cool. All right, let's do maybe a quick demo. Unless there are other questions, I'm happy to field other questions. Otherwise, I forgot to get water. How did I do that? Let me run and get water really quickly. All right. So we'll see how this demo goes. And if you're in class, like definitely come up. Oh, hang on. Let me do this. Let me pop it out so you guys can see. Oops, now it's too meta. It's okay. All right, so so we don't have pentane yet. Like I said, we're phasing out hexane for safety reasons. So we're going to purchase some pentane. So this isn't my first choice, but it's cyclohexane. So it should still be fairly nonpolar. But let's start with water. And so again, like you're also more than welcome to come up during the quiz time break and play with this yourself. And of course, water, we already mentioned, has a high surface tension. Those hydrogen bondings are really strong. And so there it is. And if we're really bored, and I don't feel that bored today, you could count them. So that would be like your objective in lab is how many drops can you get of water versus cyclohexane. But right away you can see that the cyclohexane does not bulge up. I had a hard time with my camera angle, but I think you can still tell. And still going. Oh, oh. And so you see the cyclohexane, right, kind of spills over more easily. So I did kind of spill it. Oops. Oh no, I didn't want to put that on my mouse. Try to keep organics away from plastics and such. But you can play with this and kind of look at it. But again, we just want to take away our surface tension. And so you can see that I've spilled my cyclohexane just a little bit on my penny while my water looks strong. I could probably keep going with my water, but like I said, I didn't feel that bored at the moment. But yeah, if you're in class, definitely feel free to come up and look at it. Any questions, thoughts? All right, we'll probably end here for today then. I think the homework should be simple enough. Just kind of go through it, ask questions though if things do come up. I do like the paper, so I think the paper gives you a much better understanding too of the sea of electrons rather than just a sea. All right, I'll probably end this stream then. And so it'll be quiz time. And then, of course, again, ask me questions. Ask me for help on the paper, anything else you need. All right, I'm going to stop this.